Searching is a process of finding a sequence of steps needed to solve any problem. Searching algorithms in artificial intelligence can be categorized as informed and uninformed search algorithms. An uninformed search is a brute force or blind search which has no additional information of the goal node other than that provided in the problem definition. The primary objective of uninformed search is to differentiate between the target and non target state. On the other hand, informed search algorithms have information on the goal state which helps in more efficient searching. To make the distinction more clear, let's consider an example. Suppose X is asked to go to Y's house. There are three ways which can lead X to Y. If X chooses the first path, then he gets dirty with the mud before reaching Y's house. If he takes second path, then the dog chases him and he is out of stamina. And traveling by third path is more costlier than the previous two. But all the three ways can lead X to his destination, and X is now confused between which path to choose. Now suppose the task of X is slightly modified and he is now asked to reach Y clean and energetic. Then X can make use of this additional information to eliminate the possible options from the solution set and choose one optimal and efficient solution to reach the goal. Similarly, uninformed search algorithms traverses through search space for all possible solutions of the problem without having any additional knowledge about search space. Whereas the informed search technique utilizes the problem specific knowledge in order to give a clue to the solution of the problem. This type of search strategy prevents the algorithm from stumbling about the goal and the direction to the solution. This information is obtained by a function known as heuristic function. It takes the current state as its input and produces the estimation of how close the agent is from the goal. The heuristic method, however, might not always give the best solution, but it is guaranteed to find a good solution in reasonable time. Heuristic function can be of two types depending on the problem domain. It can be a maximization function or a minimization function of the path cost. You all may be familiar with various uninformed search techniques such as depth first search and breadth first search. One of the disadvantages of depth first search is that there is a possibility that it may go down the leftmost path forever if the tree representing the search space is a left skewed tree, and hence all the competing branches are not getting expanded. On the other hand, breadth first search consumes a lot of memory if the branching factor is high and is trapped on searching useless and dead end paths. If we combine the properties of both depth first search and breadth first search, it would be follow a single path at a time but switch paths whenever some competing path looks more promising than the current one. And this is what the best first search is. Best first search is a searching algorithm which explores the search tree by expanding the most promising node chosen according to the heuristic values of the nodes. Heuristic are criteria, methods, or principles for deciding which among several alternative courses of action promises to be the most effective in order to achieve some goal. Now let's dive straight into the best first search algorithm. Let A be the start state and G be the goal state. The labels on the nodes represent the node names and the numbers on the edges represent the actual distance between the two nodes that are joined by an edge. For example, here, the distance between D to F is 25, which is actual distance one needs to cover to move from node D to node F. The table here indicates the value of the heuristic at each node. This value represents the cost pre-calculated by some formula to reach the goal state from the current state. Let's assume that the heuristic value here represents the straight line distance, which is the shortest distance between any 2 points. So, the value corresponding to D represents the straight line distance from D to G. Also, we have two priority queues as open queue and closed queue. Open list stores nodes that have been generated but not examined. This is organized as priority queue in which nodes are stored with the increasing order of their heuristic value. Closed list stores nodes that have already been examined. To apply best first search algorithm, we will first start with the start node A. The open queue initially contains the start node as the current node. The algorithm removes one node in the front of the open queue and explores that node to find its neighbors. Don't worry if this enqueuing and dequeuing does not make sense now. The process will be clear as we proceed with the algorithm. Now, the neighbors of A are B, C, and D. Since any of these nodes do not represent the goal state, therefore we will enqueue these nodes into the open list. But instead of inserting it directly, as in breadth first search, the best first search algorithm makes use of the heuristic and inserts the nodes in the ascending order of their heuristic values. This ensures that the nodes with less heuristic values, that is, the nodes which are closer to the goal node, are expanded first. Hence, according to the heuristic values, the nodes will be enqueued in the sequence C, B, D. Since the node A is now expanded, we will put it in the closed list. The algorithm now repeats the previous steps and dequeues the node from the front of the open queue and compares if it is the goal state. Since C is not the goal state, therefore the algorithm replaces C with its successors in the increasing order of their heuristic values. Hence, the open queue now contains F, E, B, D. Since C is now explored, it is inserted into closed queue. In the next step, F is dequeued and explored. The successors of F are G and D. Since D is already present in the open queue, the algorithm inserts G in the open queue and F in the closed queue. Now G is dequeued from the open queue, but since it is the goal state, the algorithm terminates and we have our path from start state to the goal state as A, C, F, G. Hence, best first search algorithm can be summarized as: let open be a priority queue containing the initial state. Loop until we find a solution to the destination node, or stop if the path from initial node to the destination node does not exist. Remove first element from the open queue. If the removed element is the goal state, then return the path from initial to the goal state, else generate all the successors of the removed node and insert them into the open queue according to their heuristic values. The path does not exist if open is empty, that is, all nodes are already explored. If we compare this algorithm with the breadth first search algorithm, then the change is at the point of insertion of the nodes in the open queue. Since the best first search maintains a priority queue, therefore, instead of exploring the node B and D after the node C, which are present at the same level, the algorithm explores C and goes to deeper level if some competing path looks more promising than the current one. And the one who guides this search is the heuristic function. Now let's have a look over the performance measures for best first search. Best first search is not complete because the algorithm may follow infinite path if heuristic rates each state on such a path as the best option. Also, the worst case time complexity of best first search is order of b raised to m, where m is the maximum depth and is same as our previous uninformed techniques. Since the algorithm must maintain a queue of all unexpanded states, space complexity is also order of b raised to m. Also, in some cases, the algorithm may not produce an optimal solution. As in our example, the path ACFG has the total distance 14 plus 10 plus 20, that is equal to 44, but there still exists a shortest path from A to G, which is ACEHG, with the total distance of 41. This is because the heuristic does not take into account the distance of the current node from the start node. Hence, to guarantee a complete and optimal solution, A-star algorithm was developed in 1972 which is the variation of best first search algorithm. If you want to know how the A-star search algorithm achieves better performance over best first search, then don't forget to subscribe my channel and click the bell icon to be the first to get the notification of the next video. Also, if you find this video interesting, please do like and share. Thank you.